All right, it's History of the Periodic Table notes. Yay, notes! He was born in Russia in 1834. See, it's just like the song. It's already right here. See, that song was great. I'm glad we got to hear that song twice. Now, he was a professor at St. Petersburg, and you will get to know this at some point in the near future when you do make it to college. The professors there, they don't make that much money. We actually get paid more as teachers in Frisco ISD than most college professors. But as a college professor, there's other ways you can make your money. And it's been happening for hundreds of years. This was back in the 1800s, early 1900s, professors were already doing this. What they do is they write their own textbooks. So he began working on his own chemistry textbook. And when they write their own textbooks, students take their class and the professors say, well, if you're going to take my class, you have to buy this book. And then they get the money for it. So it's just brilliant. So what he did, one of the things he did when he started writing this textbook was he took all the elements that were known, he started writing them down, their properties, everything he knew about them. There weren't that many elements at the time that were known, only 63. So he wrote down their properties, their names, and then he started to put them in order and started to arrange a periodic table. And there were other periodic tables at the time, or not periodic tables, other tables of elements, but he's the first one that put them into periodic trends. And what a periodic trend is, a repeating pattern. He tried to find something, some reason to put them in this order. Now, the first thing he did to order them was their atomic mass. And then after atomic mass, he put them in order of, or in groups based on their properties. So he found properties that were similar and put them in order of mass and then by properties. The periodic table looks something like that. Now, this is a periodic thing right here. I'm sure you've all seen something similar to this, yes? So everything right there has what in common?
They're all Sundays.
Those are all Sundays. Now, it repeats every time. They're all very similar. But there's something different also. If I go from this one to this one, are they the exact same? No. But do they still have something in common?
Yes.
They're all Sundays, but they are slightly different. And that's the basic thing behind a periodic table. It repeats. Everything on the Sunday has that in common, but still different. So, same properties were organized together in the same column. He left spaces for things that were not there yet. So, he actually predicted the existence of elements that had not been discovered. And that's one of the things that other scientists at the time were like, what are you thinking? There's no such thing as this element that's not even discovered. So right here is one of his first periodic tables. You can actually see the different groups. And then right here, at number 44, he's like, there has to be something there. There's something there with that mass that would have these properties. Because he already knows where titanium is. It wouldn't fit there. The mass is wrong, the properties are wrong. So he's just going to put a question mark there. We know the mass, we know the properties, we just don't know what element it is yet. He did the same thing on the next row down. And this is where most people are like, I don't know about this. And then before he died, scandium, gallium, and germanium were all discovered. They actually fit into the periodic table with the correct masses, with the correct properties. And now everyone's starting to think, oh, wait, maybe this periodic law, this periodic table that you came up with, there's something to it. But then along came another dude, Moseley. And Moseley's like, okay, Mendeleev, the periodic thing, you're dead on with that. That works. We need to order this by the trends. But something that you're off on. The periodic table is not always correct. It doesn't always go by mass. If I look right here on the periodic table at tellurium and iodine, tellurium is 127.6, iodine is 126.9. So that mass actually goes down. So we cannot put it in order of mass the entire time, but we actually need to put it in order of atomic number and still group it by trends. So Mendeleev's table was very unique because it did go the columns and rows and group things in similar reactivity, but Moseley did make it a little bit better. Next thing, the columns are called groups. They're also called families. I'll use those names interchangeably. They all have similar chemical and physical properties. Row 7, or the 7 rows are called periods. That tells you the number of energy levels. How many rings are going to be around the nucleus? Those rings are where the electrons are located. You'll probably remember that from 2 sets of notes ago. All right, now metals. Metals are the majority of the periodic table. So the majority of our elements that we have discovered are metallic. They're solid at room temperature. Yes, I know there is an exception. We do have mercury. It is a metal. It is liquid. But the majority, all the others, are solid at room temperature. They are good conductors of heat and electricity. They are conductive. They are shiny. They are opaque. Means we cannot see through them. They are malleable. They are ductile. Now, the next type of element we have on the periodic table is the nonmetal. Nonmetals are poor conductors of heat and electricity. They are brittle. They are dull. They could be solid, liquid, or gas at room temperature. We have all the above on the periodic table. And these are the second most common thing on the periodic table. So the most common is the metal. The second most common is the nonmetal. Nonmetals are to the right of the stair step. You remember the stair step when we were coloring our periodic table? They are to the right side of that. Metals are to the left. And if you are on the stair step, you are a metalloid. All right. So when we're looking at the periodic table, the first 2 columns and the last 6 columns are called the representative elements. On the periodic table that you were given, that you colored, they're actually labeled with an A after the number. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. All of these things, all these groups have the same number of valence electrons. So everything in 3A has 3 valence electrons. Everything in 8A has 8 valence electrons. Everything in 1A has 1 valence electron. So the representative elements, that's one of their unique characteristics. They all, in each group, have the same number of valence electrons. The middle elements, these are the ones in yellow right here. They are the transition elements. They do not have the same valence electrons. It varies. It changes. So the number of valence electrons in that center section changes. All right, the bottom 2 rows are right here in sky blue. These are called the lanthanide and the actinide. They actually go inside the periodic table. So they just fit right on in there where those arrows are drawn. So make sure you don't forget them. The numbers still do go in order. Now families do have similar properties. Everything in the alkali metal group is a metal. So everything in the alkali metals are metals. They are solid at room temperature. They are very reactive. They are soft. They are silver. They are shiny. They are not very dense. All right. So I told you I'd show you a video about alkali metals, and here they are. It's a quick video, so pay attention. Lithium, the top of the alkali metals. So you put it in the water, you see it start bubbling and fizzing. Sodium reacts a little bit faster. Then we get to potassium. Actually catches on fire than rubidium. A little bit better. Cesium.
No, it's okay. That's awesome!
Okay, so the cesium actually does explode. So everything in that first column, I told you they would have similar properties. Looking down the column, everything in there reacts with water. That's how reactive it is. If you put a large enough sample in there, every one of them will explode. But the cesium, even the size of a pea, that little bitty bit made the glass explode. That's just amazing. The francium, you don't put that in the water. It would still explode, but it's a bit radioactive. And you don't want something radioactive exploding around you. It's not that healthy.
Unless I turn into the whole.
Okay. Next up, we have the alkaline earth metals. Everything in the alkaline earth metals has 2 valence electrons. They are still metal. They are still solid because we know there's only one metal that's not solid. They are very reactive. Not as reactive as group 1, but still pretty reactive. I mean, magnesium makes some amazing fires. It's one of those things that you'll get to play with in high school chemistry. You'll actually take some magnesium, you'll burn it, and if you look straight at it, it will actually injure your eyes because it is so bright. It is awesome. Next up, we do have the transition metals. This is groups 3 through 12. They have different numbers of valence electrons, so we can't just look at their group number and determine valence electrons. They are metal. They are not as reactive. They are still great conductors, though. The inner transition metals. Now remember, inner transition metals, there are 2 types. The lanthanide series or the actinide series. The lanthanides are the top row. They are shiny. They are reactive. Actinides on the bottom row. Every one of them is radioactive. Most of them are man-made. Every element larger than uranium. Uranium's number 92. Every element larger than uranium is man-made. They do not occur naturally. All right. The boron family is group 13. Now we're back onto the representative elements. Boron family has 3 valence electrons. Boron is a metalloid. The rest of them are metals. They are reactive. They are solid at room temperature. Next up, after the boron family, one of the best ones, the carbon family. Now, the carbon family is in group 14. They have 4 valence electrons. Carbon is a nonmetal. We got some metalloids in here. We have some metals in here. It's a really good mixture of everything. Next up, we have, the nitrogen family, group 15, 5 valence electrons. Mm-hmm. Yes, the valence electrons across the representative elements just go up 1 each time. So group 15, 5. Group 16 is going to have 6. Group 17 is going to have
7.
It's amazing like that. So next up we do have the oxygen family, group 16. It has 6 valence electrons. Now we're starting to get more reactive. Remember when we had alkali metals, they were very reactive. Then we kind of got less reactive. Now, after we get past the carbon family, the nitrogen family is more reactive. Oxygen family is more reactive again. The next one up is the halogens. They're the most reactive on the periodic table. They are so reactive that they are always found in compounds. So that they are so reactive you don't just find fluorine out there by itself. You don't just find chlorine out there by itself. It's always in a compound. So after we get to the halogens, we have the last but not the least, the noble gases. Now these have 8 valence electrons. They are completely full. That means they don't want to react. They are unreactive. So they do not react. They are colorless. They are odorless. They're amazing things. We have the hydrogen. The one element that is so different than all the other elements, it's ridiculous. We put it over there with the alkali metals, but it's not a metal. It's a nonmetal. We put it with the alkalis because it only has one valence electron. But it's very reactive. It is a nonmetal. It's strange stuff, that one. And that does finish us off on the history of the periodic table notes. Yay, notes!